So I guess we're going to get started for the afternoon session. And my understanding from talking to Ignacio is we're going to do 3 talks. And then the speakers are going to be mercilessly dragged up to the front for a panel discussion. That only works if people ask questions. Otherwise, we sit in silence for 10 minutes, which is awkward. So please have questions and get ready to ask them. So I'm going to talk about our Harmonized Landsat Sentinel-2 project that we have going at NASA Goddard Space Flight Center, a joint effort also with University of Maryland, Louvain University, and NASA Ames. And I don't need to talk to this crowd too much about why we're so interested in high temporal resolution observations. It's pretty clear. This project actually started out as a NASA contribution to GeoGLAM, the Geoagricultural Monitoring Framework. And we recognized before the launch of Sentinel-2 that there was going to be a strong desire to be able to put Landsat and Sentinel observations together to try to get to even better than 5-day observation frequency. This is a map from Alyssa Whitcraft's PhD dissertation in 2014, which basically looks at the revisit frequency needed to obtain 70% cloud-free view every 8 days. So that's kind of the agricultural community's need. And you can see that over most of the agricultural parts of the mid-latitudes, you need a revisit frequency of on the order of 2 to 3 days, right? And if you get into the tropics, it's even worse than that, and you probably can't even do it with optical data. So that's kind of what we're shooting for with this project, is basically to put Sentinel-2 and Landsat together, as other people have talked about here, and to try to create a seamless surface reflectance data set, and to do the necessary atmospheric corrections and spectral adjustments and Brdf adjustments so that ideally the user doesn't know which observation or doesn't care which observation corresponds to a particular sensor in the data set. It's sensor agnostic at that point. And this is a little analysis that Martin Clavery did of what we could expect in terms of cloud-free revisit period with Sentinel-2A, 2B, and Landsat 8 put together. This is based off of some Google Earth Engine analysis using MODIS cloud frequency data. And we can see that again in the mid-latitudes, we're actually getting to that weekly cloud-free revisit frequency, which is pretty much what the agricultural community is looking for. So I thought I'd do a little digression and talk, since this is an ARD workshop, talk a little bit about what we mean by harmonized. So this is another piece of terminology which is ill-defined, right? We've got ARD, we've got interoperability, we have harmonized. Okay, so what does harmonized mean? There's different levels at which you can try to put data sets together. This effort, HLS, is focused on the radiometric level. So that's the lowest level where we're actually trying to munge the data together so that it looks like the combination of the two. It looks like a single sensor. This only works when the sensors are fundamentally similar in terms of their measurements, right? So Sentinel-2 and Landsat 8 are very close together on purpose. And so this kind of approach makes some sense. Not all sensors are very close together. Sometimes you have geophysical variables, and it's better to try to harmonize at the scale of the geophysical variable, the leaf area index, for example. We can get that from LiDAR, we can get it from optical data, we can get it from moderate resolution, from coarse resolution. It may be better in some cases to actually harmonize at that higher level product. And then finally, you have orthogonal measurements, which are inherently not harmonizable, right? So radar and Landsat are different modalities of observation, and it doesn't make sense to try to combine those into a single physical variable. And so in that case, the fact that they are orthogonal is actually an advantage because they bring different pieces of information to what you're trying to solve. So it's just sort of a conceptual framework for thinking about what level do you want to harmonize, and do you want to harmonize at all? In this case, as I said, we've chosen to harmonize at this radiometric level. That's not necessarily the best or the only way to approach the problem. It's just what we did, recognizing what we think users might want. So this is what we do. We take in standard L1C products from Sentinel and L1T, or Collection 1 products from Landsat. We apply a common atmospheric correction based on the source algorithm that Eric Vermote has developed for Landsat 8 and also adapted for Sentinel-2. We geometrically resample and grid to the Sentinel-2 MGRS tiling system, but at 30-meter resolution, so we preserve the historic resolution of the Landsat archive. We do a Brdf normalization using the algorithm that David Roy published about 2 years ago, which is just a fixed set of coefficients, which works if you have a limited variability in the view angle, which is the case with Sentinel and Landsat. And then we do a bandpass adjustment, which is based on a global collection of Hyperion hyperspectral data. And we looked at the bandpass for Sentinel-2 and Landsat and built a single regression model based on that hyperspectral data set. So we basically adjust the Sentinel-2 so it looks more like Landsat in that case. So what comes out of this are basically two harmonized data sets. We call them S30, which is Sentinel-derived, and L30, which is Landsat-derived. And these are basically N-bar Brdf-corrected surface reflectance. All right. Again, we're using the source atmospheric correction. This is kind of the foundation for the processing. Seems to work pretty well. It's used for MODIS, as well as I said, Landsat 8 and now Sentinel-2. It's an image-based approach for retrieving the aerosol, so it uses the red-blue ratio, but treats that as a spatially variable red-blue ratio. Okay, and so that's derived from MISR and MODIS data worldwide, and that's essentially a spatial lookup table. And what we see is, in general, the blue line here, as a function of the reference surface reflectance level, this is the error in absolute reflectance, and we see about a 2 to 6% relative uncertainty after atmospheric correction. So that's kind of within spec for even for MODIS. Our current data set is, we call it 1.4. We have 105 global test sites, including all of North America. So this is about 25% of the global land area. You can see the data volumes here. The Landsat 8 data starts in 2013 and extends to the present. Obviously, there's nothing to harmonize with it in 2013 and 14. The Sentinel-2 data starts in 2015 and extends to the present. So those are the L30 and S30 products. And yeah, so this is now coming online. I'll have a slide at the end that talks about when it's available. We put a big priority on QA and uncertainty analysis, accuracy analysis. We distinguish between the two. We consider QA to be basically flags that tell the users whether they want to use a particular granule or a particular pixel observation. And so we have per pixel cloud shadow, high aerosol bits, cirrus bits. We also have, on the granule level, comparisons with contemporary MODIS N-bar products, right? So we take our HLS reflectance product and we compare it to MODIS reflectance products from within a day or two. And if we see major discrepancies, we say, eh, something went wrong here, let's flag that and put it aside and out of the collection. Validation, on the other hand, we're really looking at the uncertainty, the bias, and the precision associated with a single observation, right? So what's the uncertainty associated with a single observation with respect to a true value of surface reflectance? We have different approaches for that. We have a bottom-up error budget based on the individual algorithm components we can rack and stack. We are doing comparisons with SURFRAD albedometer measurements, and Belen Frank from University of Maryland is doing some of this work. This is an example of broadband albedometer compared to Harmonized, the HLS albedo product. So this is basically converting HLS into an albedo by doing a hemispheric integration and a narrowband to broadband conversion, and then comparing it to the in situ data, and we end up with about a 10% relative error. But of course, there's all sorts of corrections that sort of pile on error in doing that process. We can also look at short-term variability of time series, and there we typically see about 3 to 4% relative RMSE. So that's not an absolute accuracy, but that's a temporal stability metric. And this is an example of some of the time series that come out of HLS. The black dots here are flagged as good or clear observations, and the red dots here are flagged as clouds. We see a very short growing season here in Sweden, but all longer growing season here in France, and you can sort of see the Sentinel-2 data coming in 2016 and 17, filling out that nice time series. And this point was made before, so I'll just skip over it quickly, I think by EarthCast, that this is really geared toward being a scientific data set, and in line with kind of the Landsat program, we're interested in long-term ecological change, and a lot of those changes are pretty subtle. Right? So we're pushing the boundaries of, if you want to pull out some of those subtle changes, of what you can do with atmospherically corrected data. But it puts a premium on accuracy assessment. I mean, we're trying to pull out these sort of long-term trends associated with ecological changes like droughts or recovery from disturbance. And if you have large variability around each single observation, or essentially the same, a scatter around a short time period, it limits what you can pull out and what you can identify as a real change. So that's why we put a premium on accuracy assessment. I threw this slide in after this morning's discussion. I'm guilty of throwing slides in at random. There was a discussion about Brdf adjustment, and this is a validation we did of the Brdf correction that we've implemented, where we're looking at adjacent MSI swaths from Sentinel-2 in the overlap area, both without Brdf adjustment by band and width. It's not a big difference, it's small, but on the other hand, this is a very compressed reflectance scale here, and you're seeing at least sort of 4 or 5% offset in reflectance for brighter targets in some of these bands, and mostly that gets corrected out by the Brdf adjustment. So that gives us some confidence that it's working. So just a quick tour through some applications. This is an example that we've shown before. Time series of mixed grassland and irrigated alfalfa in Wyoming. And one of the cool things about this is that we're getting sufficient density of observations between the Sentinel and the Landsat that we can actually identify individual mowing events in the alfalfa. So we're actually getting information about crop management by combining those two data. And if you just use Sentinel alone, or certainly Landsat alone, you'd never see that. And then another application was the first crop type map for Germany that was produced by Humboldt University last year. And this was done with HLS data and achieved pretty good accuracies, and I think they're continuing on with that work now. What allows you to do that kind of crop type mapping, of course, is the identification of vegetation phenology. That's sort of the name of the game in terms of ecosystems and agricultural monitoring. This is an example from Delaware, where we've taken the HLS data and interpolated it using spline interpolations to get phenological curves for 4 different crop types. In the winter, it's all kind of a mess. You might have snow on the ground. You have cover crops. But as soon as the growing season starts, everything kind of normalizes, at least in this local area, and you can distinguish even between corn and soybean, which is typically fairly tricky. So that's the key contribution that time series analysis gives you, is this sort of phenology information. And a little bit of eye candy, taking those interpolated curves and then running them across the landscape. This is a case in eastern Nebraska showing the green up through the growing season. The natural grasslands green up first, and then the planted crops green up. In the summer, everything is crazy, humid, beautiful. And then now we're harvesting, and back to the natural grasslands, sort of slowly senescing through the late autumn. So a quick, how long do I have? About another 5 or 10 minutes? 5 minutes. Okay, all right. Oh yeah, okay. So a quick example of a paper that we just did on applying HLS to crop type mapping. This is the accuracy of 3 different time series, Sentinel 1A SAR, the HLS data, and then combining the radar with the HLS. In successive colors. If you just use radar, your accuracies through the growing season never get that high for 4 sites in the US. The optical HLS data in the blue gives nice, much better accuracies. Interestingly, you don't get that much improvement in these cases, at least, from then adding the radar back into the HLS. That's not to say radar isn't useful. There's obviously, you can't map rice cultivation in Southeast Asia without it. Just in these cases, in the US mid-latitudes where cloud cover isn't so pervasive, it seems like the optical data actually is a better bang for the buck. So a quick word about our processing approach. Through version 1.3, we processed at NASA Ames down the street at the next computing cluster. With 1.4, we've migrated to AWS, and this is through the AIST managed cloud environment. And if you're into sort of AWS, this is our processing architecture. We're using CFN cluster, which allows us to dynamically create processing clusters, and we generally create about 300 spot instances. So we're using the spot market to reduce costs. And then we put the output into S3 storage buckets. And then we egress once out to Goddard for public distribution so that we're not paying the sort of uncertain egress fee. Although if you have an AWS account, you can use it within this environment, of course. The website is given here, and this also gives public access to the data sets. At the moment, 1.3 is online. 1.4 is processed, but we're shipping it over to the Goddard servers, and that'll take probably another couple of weeks. With 1.4, we're also moving to, I wouldn't call it near real time, but it's basically 5 to 7 day keep-up processing. So you should be able to get an HLS product roughly 5 days after acquisition. And availability of the atmospheric correction parameters is really what's limiting us in terms of near real time. So quickly, some harmonization challenges. The cross-calibration of the sensors really hasn't been an issue. They are well characterized and meet both their individual requirements as well as being well aligned between each other. And we've got some papers with the Landsat and EOFSAC characterization teams that explore that. Registration has been an issue between Landsat and Sentinel-2. I won't go into the details. There's a paper here by Jim Story that talks about that, but basically because of the relatively poor absolute geolocation of Landsat relative to Sentinel-2, you can get 20 to 30 meter offsets between the two data sets when you try to co-register them. And so we use image-to-image correlation approaches, a package called AROP that was distributed from USDA. And we pick out master scenes from the Sentinel-2 archive for each tile. We've, of course, had problems with mixed processing baselines. Sentinel-2 has been evolving, Landsat's been evolving, and that's always a headache for people trying to work with data. And then a big one, cloud and shadow masking. This has been brought out before, but without a thermal channel, the Sentinel-2 cloud masking is problematic. And so we've been working with Boston University to explore the different options for Sentinel-2 cloud masking, and also the next round of the CEOS atmospheric correction intercomparison experiment will tackle that as well. Just a quick example from Curtis's group at Boston. These are 5 different approaches toward cloud masking of Sentinel-2 data: Sen2 core, F-mask, a temporal version of F-mask called T-mask, the Cesbio Maya algorithm, and LeCirque. And you can see the tremendous variability in what counts as a cloud. I think we were convinced that LeCirque is actually correct in this case, because if you look at the cirrus band, this area, although it doesn't show it in this RGB image, is covered in cirrus. So it just goes to show it depends on what you want to call a cloud also. There's, the reference problem is there as well. And then finally, some reflections on ARD. A lot of people have talked about what constitutes ARD. Agree with all of that. One of the things I did want to mention, though, is that what does it take to get to science quality ARD? I think the validation of level 2 reflectance products really remains a challenge. I mentioned the AKIX intercomparison experiment, but if you followed that, they rarely validate surface reflectance itself. They're actually validating retrieval of aerosol and then assuming that the surface reflectance is correct after that. It seems to me that we've got in situ measurements like RadCalNet and other comparable systems in Australia and Europe. These now, I can't imagine, they must be able to be extended spatially by UAVs so that we get to Sentinel-2 and Landsat pixels, right, and fully characterize that pixel. And could we have an open source library of reference for L2 validation that would work across not only government programs but the commercial sector as well? I think that would be an exciting kind of contribution to make. So status and future directions, 1.4 is being released this summer. As I said, it's being transferred right now. HLS is supporting a NASA program called Muesli, which is producing continental scale products. They're listed here. And then there's the option for a global production starting in 2019. So I think that's it. And I'll leave you with a picture of Delaware Bay. This is the canal that connects the Delaware Bay to the Chesapeake so that you can flee New Jersey and get to Delaware. All right, so that's it. Thanks.
So we're going to get the next speaker. Curtis, are you on the same computer? Yes. Wonderful. So the idea here is we're going to go through the talks fast, and then we're going to ask the speakers to come to the front, and then we'll take questions together about the talks. We're going to do this in sets of 3 talks. And the idea here is to have a little bit of an intimate kind of discussion about the presentations with all the speakers at once. So that's why we have this cozy seat arrangement here. Okay. All right.
How's that? Okay, thanks. I think I'm safe making my admission because Chris isn't in the room that I'm exactly the kind of person that he tried to keep from coming to this meeting. These are the people who actually do the work, not me. And so anyway, that's the way it is. It's sad but true. What I'm going to try to get to is really my key point, which is anything that'll improve the temporal frequency of our observations is a huge help. And so ARD in my book is all about temporal frequency. This is a slide I've been showing for about 6 or 7 years, and this has sort of been the mantra for my life during that time. What are my goals? Reconstruct the history of the surface of the Earth and start providing information about surface change in near real time, so we start making it management relevant instead of just sort of historically relevant, and it takes the same kinds of approaches actually to do both. So that turns out to be quite convenient. And all this work sort of came out of the explosion that happened when Landsat data became free. So we started to use all the observations in essence rather than just a few of the observations. And what's nice is that you don't rely so heavily on individual observations when you do that. And that's been one of the real lessons that has come out of all this. You have to take seasons into account. You have to be good at screening out noisy things. But there's a lot of that. Now, to cut to the chase, the way we approach this problem of doing sort of continuous monitoring of land cover and land cover change, you accumulate all the images, try to filter them as best you can, use surface reflectance, and we fit time series models to each pixel. And so we're in sort of the model fitting business to these time series over long time periods. And then to find change, we don't compare images to images. We compare new images to predicted images or predictions that we expect based on our time series models and that sort of thing. And we live then in a world of time segments and breaks and time segments, and we classify entire time segments rather than trying to classify observations. That gives us a tremendous amount more information for doing the classification part of this. And just simple examples of what these time series look like in the near infrared as you go from places with dramatic change to a little change to no change. You guys have seen a lot of this stuff. Subtle changes like pest infestation show up very easily and clearly. This is sort of examples from up in Canada of things like fires and thinning and that sort of thing. Now, Jeff showed you interpolated values between images. We have a model, so we can, in essence, predict what an image would look like on any day. And so this is, in essence, a predicted Landsat image, in this case, over the course of a year. And so certain areas green up soon, certain areas green up late. You can sort of track these. And these become the basis, then, these predicted images of our whole change detection process. And can be used for more than that, too, I think, as I'll try to get to. Now, so we can produce, as I just showed you, the last one was kind of a false color image. This is a true color image. But you can produce a synthetic, what we call a synthetic image, which is these predicted images, for any day of the year. So I'm going to show you sort of series of images for the same day of the year so that you don't see a lot of change between this. So this would be, for example, a synthetic image in I'm going to show you an animation. I want you to get used to the rhythm. 1985, show you the next year, 1986. The only place the image changes is where we've identified a change. And so, and then in those places where we've identified a change, I'm going to show you the change not in some categorical way, but the change is going to be in tasseled cap brightness, greenness, and wetness, where the brightness goes into the red color, greenness goes into green, and blue goes into the blue. And so there wasn't much change, so you didn't see much there. So then we're going to go back to 85 and then go to 87 and accumulate change and pace all the way through. And so if you go all the way to 215, this actually is a couple-year-old animation because it only goes through 2015. Then you see the change. And so the places that have gotten very red are the places that got very bright. Places that have gotten greener or this sort of cyan color forests as they're growing get both greener and wetter, and so you get kind of a cyan color that comes out of the whole thing. So this is an animation. If I get this started, I can stop talking. It'd be sort of nice. This is just a year's worth of Landsat 8 images to get you to realize that there are clouds and seasons, and you have to sort of build both of them into what you're doing, and that's sort of the basis of what we're using. It looks kind of ugly at times, right? But in essence, that's at the heart of what we do. And then now we're going to go through this sort of sequence. This is my backyard, so this is Boston. This year where we go through 85 to 89 and what's changed, and the colors represent then the kind of change that have occurred. And so this takes a minute to sort of step through this. One of the things about our change detection methods is that we typically find that you have to use something like find the change in like 5 consecutive observations or something like that before you actually believe it. That a lot of the noise is quite ephemeral and the change is more persistent. And so in essence, how frequently you have observations will dictate how long it's going to take you to be able to find change. And so that's part of the reason I'm so interested in higher frequency of observations. And so as you can see, we accumulate the change through time, so more and more of this area it has started to show up as change, and you can start to get some sense of how the landscape overall has gone and changed. And in a minute we're going to go to an area that's zoomed up a little more so you can actually kind of see what's going on rather than kind of try to take it in over a large area because it's kind of hard over a big area. And so now this is just kind of repeating the same process. This bright area in the middle is an old quarry. And one of the projects that went on in Boston over this time period was something called the Big Dig, which if you're a taxpayer, you may know something about. It's the largest single public works project in the history of the country, at least it was at the time, and it was to take one highway and put it underground and run some tunnels to the airport and stuff, and it's great now that it's done. It only took them 16 years and that sort of thing. So there had to be some place to put all the stuff that they dug out to put these things out, and they started by filling in this quarry, and then now like here they started expanding it, and they in essence changed the whole area by filling it with all this stuff they dug out for the Big Dig. And what's interesting is you watch it through time. At first it shows up in this sort of bright red color because it's brighter than the old forest. But eventually they built a golf course on top of it, and so then eventually it becomes greener than what the original forest was. And so the notion of using this change in brightness, greenness, wetness, it's always relative back to you can see it start to green up now, and so you can start to see the change in what the colors are for the change in the condition. So it's sort of fun from that sort of way. But I think you sort of get the idea that you can do this. We're going to do this now basically for the whole United States as part of a program called LC-MAP from the USGS. Anyway, this is another place. I don't think we need to go through a whole other place, but you can kind of watch suburban development go on. It's sort of fun to watch. The roads go in and then they build the houses, and anyway, you can see that sort of stuff. Now, why more frequent observations, and why is it always about more frequent observations as far as I'm concerned? Here's an example from one of my students, Eric Bullock, who's working on forest degradation in the Amazon. And if you look at the NDVI time series down here, you would never know anything happened. It's too noisy. And he uses this NDFI index, which comes from Dara Roberts and Carlos Souza. And this event, you can only see for a very short period of time, right? You can only detect it. And initially there was probably what was one cloud observation that was missed. And so this notion that you've got to see it multiple times and they only last a short period of time in order to be convinced is why, again, why I'm after as frequent observations as possible. I have another, ex-student now. She's graduated. They do occasionally graduate. Val Pasquarella, that we started to have gypsy moth problems back in the Northeast after many years of not having any. And one of the values of having kind of a running model of what you expect the surface to look like is you can recognize when things don't look right. And so in essence, she's been putting out now annual maps. The map for this year hasn't come out. But we also are doing this at monthly time scales for producing maps of forest anomalies. Something's happened. We aren't necessarily going to dictate what it was that happened, but these are the places where we're seeing differences from the past. Monthly is about what we can do with Landsat data, and maybe we could do every 2 weeks with Landsat and Sentinel. You know, maybe if we can add other images, we can start during the growing season doing it weekly. And then these go to, in essence, the managers who know where the problems are as they're emerging and can start to track and pay attention and hopefully eventually try to mitigate some of these damages that occur as a result of these things. So my message, I guess, or what I'm trying to get across is that I think there are a lot of advantages to, in essence, carrying a model of what you expect future observations to look like. So that when you get new observations, you don't just look at them independently, you look at them relative to what you expect. It can help with radiometric normalization on an image-by-image basis. It can also improve cloud and cloud shadow detection because, in essence, you've got a reference against which you aren't just looking at a single image. And Jeff showed you one example. I guess I have another one I'll slip in real quick. The other is that once you have a running model like this, for example, built on Landsat or built on Sentinel, that sort of thing, the requirements for how many and which bands you have and that sort of thing get reduced the more observations that you have. So we could easily live with fewer bands for more frequent observations as long as we've got good reference things from things like Sentinel and Landsat. And so I think there's relevance here there. You don't have to produce exactly what is there. Now, this is an indication for the comparisons that we did for these Sentinel things that Jeff talked about for cloud and shadow screening. And the thing that we found is that our multi-temporal method, something called TMASK, really where the benefit comes from that is for shadows, right? Because shadows are often by far harder than clouds to try to find in these images. And so here's just an example of a place where there are cirrus clouds casting a partial shadow, and unless you knew what that place looked like without clouds, you would never find it as such. And so the multi-temporal part helps with the shadows. Now, my 2 cents on the whole ARD thing. I think it's helpful right from the get-go to acknowledge that analysis-ready data is all about the time domain, that pulling in all these different sensors is really about increasing the frequency of observations, and that's the main benefit that comes. Data policy is going to be critical to the whole process. If you can't get access to all the different sensors, then it isn't going to work. I would define interoperability somewhat differently than it's been defined so far. I've heard people say, for example, I don't think of it so much as a matter of expecting to get the exact same results from the same analysis of 2 different kinds of imagery. I think that's asking too much. Instead, what I define it as is a matter of getting better results from using multiple kinds of imagery. Why bother with the individual results from individual images? You take individual images from the same sensor and you're not going to get exactly the same results that you would get for individual algorithms. So I think this is a little bit more realistic. And in terms of the path forward for the group, I would argue that the initial focus ought to be on the spatial domain, consistent geometry and projections across sensors, for 2 reasons. One is that it's solvable, right? All we have to do is get everyone to agree and work off of the same sort of coordinate systems and projections, okay? So it's a solvable problem. The spectral radiometry related stuff, calibration and Brdf correction, there's always going to be more struggle to agree on exactly what that means and how to do that. The other point that relates to that is that it will become easier at times to use data from multiple sensors to solve, for example, the Brdf correction of an individual sensor. Rather than take an individual sensor and an individual set of observations, why not use all the other observations of that place that may have been collected at different angles and use them as a way to learn what the Brdf might be at a surface rather than use some standard correction that applies the same correction to every place. So I think there's additional benefits to using all the data from all the sensors. Now, part of this question about interoperability, just to show you how bad it can get, Landsat 5 and Landsat 7, this is Jeff's questions about long-term ecological change, climate response of vegetation. This is for forests, boreal forests in North America. The near IR band between Landsat 5 and Landsat 7 aren't close enough to each other to be able to allow this, right? If those aren't going to be good enough, what is? You kind of shoot yourself in the head, because in essence, we get a different answer for which places we see trends just as a result of minor differences in the near-infrared band between Landsat 7 and Landsat 5. And so as a result, for these kinds of things, you have to be really careful. Yet, we consistently use them in time series analysis where we assume the observations are noisy. So it's not like they aren't useful together. It's just a matter of the question of exactly what you're asking of them. Landsat 7 and 8, there are bigger differences between the near-infrared bands. Landsat 8's near-infrared band got narrowed to remove a water absorption feature. In arid parts of the world, good clear atmospheres, they look very similar. In more humid places, there are actually differences. So you can't really build a single correction between the two. It depends on the conditions in the atmosphere at the time. But again, the differences aren't so bad that we can't use them in time series. And there are ways to correct for this in time series. You can include a dummy variable for something like Landsat 8 as opposed to the others and still do our time series kinds of analysis. Oops, I got a bad file up here. So anyway, this is just a repeat of the earlier slide, and it's about trying to sort of capsulize this notion of what's beneficial about having sort of these models as you go through. Thank you.
Don't say anything too offensive. All right. Sounds like you guys can hear me, right? Okay, so are we still good? Okay, so I'm Mike Humber. I'm here from the EOFSAC. I've got a little asterisk here because I'm actually lying to you on the title slide already. As of Sunday, we're no longer EOFSAC. You stand for Earth Observations for Food Security and Agriculture Consortium. We are now the Harvest Consortium as of 2 days ago, so we don't have no logo, so I took the liberty of making my own. So this is us now. I'm sure that'll change, and I'm sure that'll annoy the other 3 authors on my title slide here. But anyways, so throughout the slide deck, I'm just going to keep using EOFSAC because those were the slides I made on last week. So the motivation of this program, and what I'll do is I'll start talking about the program for a couple minutes, and I'll hopefully get into stuff that's a little more interesting and a little more conversation starting for our panel session after this. But just a little bit about the program itself. The goal of this is to enhance food security and resilience, drawing on Earth observations data, so really pushing the use of EO and satellite observations in order to answer questions about food security, resilience, agricultural systems. So a couple of things that have sort of made it around the web a little bit that are some of the more popular outputs. We have the EMS Market Monitor and the Early Warning Crop Monitor. These are 2 reports that are published monthly using Earth observations data within systems that are funded by the EOFSAC program. So the program itself is a NASA Applied Sciences program run out of UMD, launched last November with 5 years of funding. It's, as far as we know, the first NASA program office being run outside of a NASA center. And again, the goal here is really to push the use of EO in order to sort of strengthen the science behind agriculture and the food security problems. So this is essentially NASA's contribution to GeoGLAM, which we've heard that term thrown around before. It's the Group on Earth Observations Global Agricultural Monitoring Initiative. So the approach that we take here is really starting with EO data and then trying to handle that in a way that we essentially at the end make it easier for improving decisions by our end users and improving decision making. So this is driven by stakeholders, end user needs, and this is something that will hopefully come through a little bit more in the next couple of slides, where we're interested in how do we provide data in the most useful format possible. So part of this is we have to leverage existing partnerships within the agricultural and food security communities, and then also increase linkages across different agencies, across different NGOs, so on and so forth. So our group right now is consisting of over 40 different partners. Here you'll see quite a few are represented in this room. We work with public sector, private sector, government, NGOs, so on and so forth. So a lot of different groups are represented by this consortium, and again, the role of UMD is really sort of a coordinating role here. We're not taking the primary research lead on some of these projects, or most of these projects for that matter. So just to give an idea of the geographic distribution, these are where our partner organizations are located. I think we're missing a couple in Southeast Asia there, but these are headquarters locations. This isn't necessarily where we're working. These groups all have projects spread out across the world. They have pretty much global coverage for just about all the topics we're investigating. So within the context of this meeting, I have a slide about expanding partnerships here. Again, focusing on EO, agriculture, food security, that's all nice. But what I really want to key on a little bit here is this next box here. So the coordination and our collaboration with other people within the group and outside of the group. Can we share our resources? Can we use and leverage the technologies we have and our experiences and our expertise? And then can we collaborate on these research questions? And this is very important for us in terms of ARD because we need to be able to enable this free flow of data and information within our own group and then to people outside of our group. So part of how we want to do this is what's called the EOFSAC portal. So my job is I'm the lead developer on the EOFSAC portal and a lot of the other data and sort of knowledge management systems within the consortium. I guess EOFSAC portal is kind of a misnomer now. Harvest portal, that sounds a little weird, but we'll roll with it. So the goal here is to provide access within our group and outside of our group to visualize data, do some basic analysis, and then distribute data. So you can see pretty clearly just based on the goals of this that ARD is kind of the foundation of how this system is supposed to work, how we bring in information into our system, and then how we redirect users to those data sources as well. So I don't want to get too far into this. This is just sort of a high-level overview of how the system will work. We don't want to replicate data. We want to bring people in and direct them to where they can go find that data rather than creating redundant data stores within our own system. So this is something that could potentially be cloud-based. Right now we're talking about just outsourcing the data back to the original data creators and data providers rather than remaking it. Part of the reason is because we don't want to steal their hits because people's funding is tied to how many people are downloading their products every now and then. But also, it gets expensive to keep all this stuff on-prem, and it also at some point gets expensive to keep in the cloud as well. So we want to provide some analysis tools without necessarily duplicating everything. So just to give you an idea of the kind of scale of data that we want to bring in here and where we hope to get it from, these are all potential data sources. These are just collections of different places where you could hopefully find geospatial data. So FuseNet Data Warehouse is being put together right now, should be released soon. A lot of good information on socioeconomic data, things like that. The Crop Monitor and GLAM are both systems that we have at UMD, so that's pretty easy. Early Warning Explorers supports the FuseNet goals, and they stick to a lot of the OGC standards and things like that, so that's pretty straightforward. Then we start to get into some of the things where these are not necessarily geospatial data, they're not necessarily distribution ready, things like that. And these are things that maybe we have to bring in and process. It's not as easy as setting up a link to a WMS server. So the goal of this is, first and foremost, we want to interact with the existing systems. Again, avoid duplicating everything. We want to, in this sense, provide visualization. We want to host services that are OGC compliant so anyone can come in and use them and download the data from us. And then we also want to have some simple analysis tools, and we can kind of decide what these are as it, as it starts to make sense interacting with our users and seeing what they need, what are the formats they want, things like that. So again, this whole system is relying on that concept of analysis-ready data. So we can do a little bit of light pre-processing, but we don't want to do much more than that. We don't want to be fundamentally altering the data that goes into this system and providing something different to the people that are using it. So it brings us to the question of what is analysis-ready data for us. It's sort of a big question, and definitely why I'm being up here talking. Analysis ready means a lot of different things to a lot of different people. So we have different types of users and things like that. So we have to cater to a wide variety of users across different parts of our data delivery chain. So here I'm throwing up these terms analysis ready, but then also applications ready. And this is maybe something we'll hear a little bit more from the CIAS talks afterwards. This sort of ARD plus, where we're sort of drawing a distinction between what's ready for analysis for a user to come in, download it, process it however they need to do it, versus what needs to be ready on a consistent operational basis. So there's actually a very important distinction there for us as an operational programmer. We need to make sure that we're delivering consistent data in a timely manner. So at the first level, and these are not really in any sort of particular order, I would say, not any order that matters, we have product generation. So this is something we do within our program for the GLAM system, is we bring in NRT data from Lance. We bring in the surface reflectance, and we create our own NDVI composites from that. In that sense, ARD for us means that we just have the surface reflectance data in the grid delivered when we need it. This is something that, for us as remote sensing users, we're not afraid to sort of dig through the surface reflectance, create our own composites, things like that. A little further downstream, maybe we have modeling users that are using our NDVI data. And I should emphasize that this is from our perspective. This isn't universal or anything, but this is just how people interact with our data. We have modeling users that can use that same NDVI data for like yield modeling, productivity modeling, water resources allocation, things like that. And generally, they need something that's a little bit more refined than just the surface reflectance. From there, we have what we call the next users. So these are the users that don't want to process the raw imagery. They don't really even want to process the NDVI outputs, but they use the outputs from our system as information that goes into their reports that get published downstream. So the example here I have is from CONAB, and I'll show a little bit more in-depth example of this in the next couple of slides. CONAB is the company in charge of monitoring the agriculture in Brazil, and they use our system for creating graphics for their reports. The CONAB analysts do all of the crop analysis work, but they're sort of insulated from having to do the remote sensing side of it because we handle all of that in the previous step. And then lastly, we have what we're calling the end users, or the decision makers, quote unquote here. They rely on the output from the previous users. These are not people that you want to give that raw satellite data to under any circumstances. So you want to give them a very distilled source or a distilled form of information that they can go read through, and then that's just another data point in the decision-making process for them. So on top of this, sort of multi-level, multiple levels of analysis-ready or applications-ready data that we have, we also have to deal with the practical considerations of we have different spatial resolutions, different temporal resolutions, things that everyone here has already been talking about. So for us, we work at the field scale. We have projects in Tanzania and Texas working with Stanford, IFPRI, Texas A&M. We work at the subnational scale with companies like Swiss Re doing crop insurance, things like that. We work at the national scale doing crop monitoring for the entire countries of Tanzania, Kenya, Brazil, Argentina, and a couple others. And then we also work at the regional to global scale, synthesizing all that information from actors within each country who provide us with that information. We summarize that in a report, like in the crop monitors. So just as an example of how this works in practice, I'm going to talk about the Brazilian GLAM system. So this is essentially a tool that we use for delivering NDVI data to CONAB. It's a tool that's kind of evolved over the years. It's been at Maryland for, I would say, around 10 years or so. And the goal here is really to enhance the analyst's ability by lowering the barrier to entry, doing a lot of the heavy lifting in terms of the image processing before the data makes it to them, and then they can make decisions based on that. So the outputs of this often go into national crop monitoring systems or monitoring reports. So on our end, the system looks a little bit like this. This is a little bit outdated, but we have sort of this three-tiered image processing system. We have the near real-time component, an intermediate component, and then the official products get pulled in at the end when they're available. So the first one happens with maybe 1 to 2 days latency between the acquisition and the time it reaches our system. Then you have maybe 3 to 5 days, and then 5 days and up for the official product. So the system looks like this. This is just our front-end interface. It's a little dated at this point. We're working on generating a global system that'll have a completely updated front end and be a little more user-friendly. But this is the type of output that you get from the system. So on the left-hand side, we're looking at NDVI anomaly. It's masked by the wheat areas in Victoria and in Australia. And on the right-hand side, we're charting the mean NDVI values, the min and max for this area, and then the current season. So output like this ends up into the Brazilian GLAM system in the forms of these monthly bulletins. These are published every month, sent out by email and published on the CONAB website. They also take some of the CSVs that we generate and put them into their own internal system known as CIMASA. So the output of our system is actually the input into their system. So for them, the analysis-ready data is that CSV. It's not the actual NDVI file anymore. So that report just kind of looks like this. On the left-hand side, I know you can't see it, but this is just histograms of the NDVI values. This is the values moved. If you get more values to the right, that means you have higher NDVI, theoretically higher yields. As you have them shift to the left, you have lower NDVI, lower yields. So in this workflow for us, ARD is that daily gridded surface reflectance data. We create our own index products. We have certain compositing requirements, so we can be either more or less restrictive on what we call a cloud or what we call high aerosol than they were in the official products. But right now for us, sensor interoperability is an issue. So we have to display our Aqua and Terra and our VIIRS data separately because we can't just create one composite of all three sensors. There has to be work done to sort of, especially from MODIS to VIIRS, to harmonize those time series because we're running low on time with MODIS. So essentially, we've got 3 to 5 years until we have to start moving into VIIRS only. For CONAB, ARD is this NDVI time series, ultimately in the form of a CSV with NDVI values per region masked by crop area. So again, this is from our perspective. The types of analysis-ready data that we have are these EO data products. These are, for us, surface reflectance, cloud screen, BRDF corrected, gridded georeference file format through metadata cataloging. From there, we generate our indices. So these are kind of the ARD plus applications ready data. So these are simple calculations. The difference here is that this is not the surface reflectance data, but if a user wanted to go and create their own version of it, we could give them the data. They could very simply recreate that. From there, the next level up in terms of being more complicated is the satellite-derived or modeled products. These are more difficult calculations, not necessarily something that you could just go through and calculate yourself. There's a lot of intricacy into how these are calculated, something that a user wouldn't create on their own. But we still keep that theme of gridded georeference, consistent file format, metadata cataloging. But examples of this could be rainfall or burned area where the model is not straightforward to implement. And then lastly, once we get out of the spatial framework, we start talking about the tabular data, sort of derived from the above outputs. But in this case, we can be talking about things that are aggregated into units where we just have sort of a lookup table and not necessarily the spatial information anymore. So the challenges that we see in ARD, the first is context. So this is something that came up in a meeting in February at USDA. Right now we have more sensors than we've had before. They're doing a better job at actually detecting surface phenomenon. But the problem is we don't have this long time series, so we're lacking the context. If we have field scale data at 5 meter less, 3 meter, 0.3 meter, whatever, if we have no point of reference from the earlier years, then it makes it kind of hard to understand what is the difference this year versus 10 years ago. So there's been some work to do this. Van Gogh has been working on this at USDA with Martha Anderson and others, essentially trying to synthesize a daily Landsat product at 30 meter resolution by integrating the MODIS time series into that. And the results look promising, but it's still very computationally expensive. They haven't got it to be operational as far as I know at this point. The next issue we have is continuity between sensors. So this is something Curtis had touched on a little bit. The difference is the subtle difference between Landsat 5, Landsat 7, Landsat 8, and then moving into 9, then Sentinels to A through Z or whatever they get to when they get past Z. Then we also currently are sort of faced with this MODIS-VIRS transition. I had mentioned that we've done some work looking at the difference between MODIS and VIRS, and we found that VIRS is kind of comparable to, I think it was Aqua, but not so much to Terra. So it's not exactly you end one and just plop another one in. Geolocation is another big one. We've seen a couple examples of this, the small shifts in the Sentinel-2 data that need to be corrected out before the data can really be useful. David Roy, I know, had done some work at this, and there have been a lot of other examples here. I know for the work that they're doing at South Dakota, it's an issue when you're doing burned area detection because slight shifts in the actual location of the pixels when you're doing change detection, can actually cause a very big problem when you're looking for stuff like burns. And then moving to finer scale UAV matching to the high-res data that we're working with in Tanzania. Just a couple more here. So in terms of spectral resolution, the surface reflectance is nice, but it becomes a question of what are we really measuring? And I think listening to what Curtis was saying, I think that my first reaction is maybe we're talking about different things, but now I think that actually we kind of agree here. So in terms of interoperability between these systems, and let's see if this thing works here. We can see this Maris signal here in sort of the reddish part of the spectrum versus, say, the MODIS and spot vegetation spectral responses here. These are not really measuring the same thing. That doesn't mean that we can't use the data interoperability, but we have to be kind of aware of what we're actually measuring with these different systems. So maybe we can harmonize those in some way or figure out a way to sort of, like Jeff was saying with the bandpass type of idea, sort of synthesize the spectral response of one from another. But at the very sort of foundational level, these are not measuring the same part of the spectrum, so we have to be aware of that. And then the other thing that I think is sort of something we need to think about in terms of ARD is this propagation of error. So just because we have a data set that's ready for analysis, that doesn't mean that the data set is perfect and it's error-free and we can use it and expect to not have horrible results downstream. So the users tend to just go in and pull whatever product, do their analysis on it, and not really worry too much about their errors. So I work on the MODIS burned area product collection 6, and you'd be amazed how many people just go in and download the product, do their time series analysis, say there's all these changes in the fire regimes, but they'll do this for agricultural land, but we know for a fact, and it's been published, that we're wrong about 95% of the time in agricultural areas with burned areas. So it's something that we need to maybe make more clear as we go forward, as we provide easier access to this type of data, making sure that the user understands what are sort of the risks involved and just using it out of the box without questions. This was a slide that was kind of thrown at the last minute. This is talking about the multi-mission constellations. Right now, I think with the HLS, we're kind of at this scenario number 5, Landsat 8, Sentinel-2A, Sentinel-2B. Here we have what are sort of the best case scenarios if we have multiple sensors. So this slide was from Alyssa Whitcraft's PhD also. This was right after the sort of failed launch of CBERS. So we're looking at Landsat 8, Sentinel-2A, Sentinel-2B resource set 2. So this is AWIFS. You could also add in the new CBERS 4 here. So in theory, we could have less than 1 day revisit if we were to harmonize all these sensors, but there's obviously a lot of work that goes into it. You don't just simply overlay the surface reflectance on top of one another and you have a continuous time series. So those are the challenges. Now for opportunities, we actually have quite a few. So we have this increased access to data, tools, computing power. This is a good trend in general, but is especially beneficial in areas where we're sort of lacking infrastructure. If we need to do something in Kenya where we don't have the greatest internet connection, moving things into the cloud actually is very beneficial for us. We have the availability of analysis-ready inputs is sort of key to this food security monitoring issue because we can just bring in the data. There's a lower latency. We can identify issues faster. And at least in our experience, this machine learning machine learning methods, they really want ARD. The faster you can integrate these new data sets into the machine learning methods, the more rapidly you can iterate over different machine learning models and improve your results. We also have a chance here to curate and reduce the data misuse. So this is kind of what I was talking about with the accuracy. But we also need to make sure that we have someone who's sort of guiding this and setting the standards, and maybe that's something that we try to accomplish in this room this week. But are these standards set across fields? Are they set for just general EO? Is this something that CS takes care of? It's something that GeoGlam is specific for agriculture. But along that vein, we need to be kind of careful not to over-standardize. So I think some people have kind of thrown out this idea that maybe it's surface reflectance is sort of like the core ARD data set. I'm not saying it is or it isn't, but we also need to think about how far, what level of abstraction do we take that to. So if we have surface reflectance from Landsat, not the same as surface reflectance from Sentinel. So we have to think about what atmospheric correction algorithms do we use. Do we use LISRS? Do we use 6S or 7S or how many S's we're up to? AtCore, Cent2Core. All different algorithms, and there has to be some sort of standardization if we're really talking about making these data sets completely uniform. You also have ground sampling distance as you start to look off nadir, things like that. Data cubes, these look like they're sort of the real deal, right? There's a lot of good work being done with this. Google Earth Engine is sort of, I guess in a way, a data cube. Maybe Tyler can correct me on that later. But what's happening here is that these data cubes are effective tools for maintaining and providing access to analysis ready. And then we also have to ensure that we have this sort of error quantification within ARD. We need to be able to trace the propagation of error through our workflows. So I just have a couple more slides here. The first one I talk about is the cloud. Is it for everyone? So I think a lot of things we've talked about so far the past 2 days have been sort of centered, at some point, sort of cloud dependent. I think the step 0 is to just create an Amazon account or a Google account for a lot of what we talked about, and that's good in theory. If everyone goes all in, then costs go down. You don't have to pay for egress across the same Amazon region, for example. Relative to sort of your local hybrid cloud models, if you're not worrying about those egress costs, then certainly the costs go down, processing times go down. People start developing more open source tools. That's all great. But there's some cases where the cloud just doesn't fit. So the GLAM system that I was talking about earlier, this is an on-prem system. We could move it to the cloud. That's not really the barrier. The barrier is because we're on soft money. If the funding dries up for 2 months and we're on Amazon, the switch goes off and the system disappears. Right now, the way it is with the on-prem, if we run out of funding for 2 months, then as long as we don't have some sort of catastrophic hardware failure, then the system kind of lives on. We live to fight another day. So for long-running systems where we're on soft money, it's kind of an important consideration for us. But on the plus side, there's still a lot of room for innovation. So the cloud-optimized geotiffs are really nice. Data cubes are looking pretty good at this point. But I want to throw out one more word of caution here that just because you can make a map, that doesn't really mean you necessarily should. So I've quote, this is a danger of ARD. I think it's actually a great thing in ARD. The barrier to entry is very low when you have something like a Google Earth Engine and anyone can go in and write some JavaScript and get a result. That's a great thing. But the downside of that is it becomes very easy to make very bad maps. So we'd seen the quote earlier today about someone's grandmother able to make a map and that goes up on Twitter. Well, that's great, but we live in the viral internet age. Someone picks that up, and do you really want someone's grandmother doing your geospatial analysis for you? So I think that we have a responsibility to validate everything that we make and we make public, just to be sure that people understand all the risks involved with creating a map and not validating it properly and using those in the downstream analysis. So just to summarize here, I think that ARD intrinsically means different things for different users. We have to make our requirements for ARD to be general enough that it's useful for people, but not so specific that it's too restrictive. We have to provide context for our satellite observations, and the data users really need to understand the limitations and the accuracy constraints of the products that we generate. So in this sense, the who is critical. Who's defining the data? Who manages the data? Who makes the data? who generates all the results. So that's all stuff that we need to, I think, keep in mind when we're talking about area. Okay, so if you need to get in contact with us, that's it. For now, our website is eofsac.org. We'll keep it pointed even after we switch to Harvest, just to, because we don't move that fast, frankly. So.
Right. So I want to invite the presenters to the front, and now we're going to be taking questions and have a panel. Yep. Oh, you can keep your mic. Okay. All right. Any questions? I want to open the floor now for questions. Yeah. Okay.
I wanted to start the conversation with a little bit of discussion about interoperability, not in the context of radiometry, but in terms of NDVI. We saw lots of NDVI plots today. NDVI from different sensors, because of the differences in the spectral bandwidths, leads to differences in NDVI. I'd like to get a discussion going about the interoperability and maybe, dare I say, standardizing on what is NDVI. It's kind of a meaningless number in many ways. So I'd love to hear what your thoughts are on that.
Well, my thoughts were that it very much depended on what you were trying to do, whether or not those things mattered. And so I'm not sure how to go about standardizing an answer to, what counts as NDVI and what doesn't. For time series models, it isn't so sensitive. For long-term trend analyses, it is. And so there's kind of a whole variety of answers, I guess.
Well, I'll give you an example. Sentinel-2 carries 2 NIR bands, and you get a slightly different result in the NDVI from using one NIR band versus the other. And then when you start to compare Landsat and AFS again, how do you cross-calibrate these between the different sensors or between the different bands?
So I mean, typically you either, so it's a bandpass question primarily, right? So you can either try to develop SBAF routines where you adjust the bandpass like we've done. I mean, the dirty secret is, which I didn't say in the talk, is that none of them work all that well. My personal opinion is you're better off trying to fix a set of bandpasses that are common among sensors at the hardware level, and then you've, at least for red and near infrared, if you can do that, then you've sort of solved that problem. So that's one approach. The other approach is to calculate the NDVI and develop regression models between different sensing combinations. And I think those are about the only things that you can do if you want to mix NDVI. So why do you say NDVI is useless?
I didn't say it was useless.
Oh, okay.
You said, come up to the microphone? And I would invite people if they want to line up.
No, you said it was meaningless.
So no, I said it's a unitless number.
Oh, unitless. I'm sorry.
All right, in the sense that there's no standard. It's not a radiance or something else that has a standard definition. All right, and so my question really is how do we address the interoperability between all the different sensors, MODIS, all the way through to Planoscope, to high-res, to whatever else? How do we agree on what is interchangeable and interoperable? I'll just pick on NDVI as kind of the proxy for all of the different things that we want to derive out of imagery. And how do we deal with the fact that we have these different spectral band passes of the different sensors out there?
Yeah, let's see if you guys can hear me. I think Jeff was kind of getting at something there with dealing with it at the hardware level, because when we start to calibrate between the reflectances that we see from each sensor and at the image level, calibration is essentially a model. Models have error, and we start to introduce error. So what are we doing introducing, say, 3 to 5% error into our measurements when, what's the point of having 12-bit radiometric resolution when we're introducing 3-bit or 3% error into it,
I guess one way I think about this is are you interested in comparing NDVI between places or between times? Because if it's for the same place between times, you can start to learn what the differences are between the sensors from repeated observations of the same place. And so you can start to account for those sorts of things. But between places, that becomes kind of a different question. Did you have one of those in mind?
I have both in mind.
You had them both in mind, okay.
So one of my main areas of concern or interest, I maybe should say, is at global scale. How do we treat sensors in an interoperable way? NDVI is a proxy again for all these different things we want to derive out of imagery. Do we want to deliver to users in an ARD sense, interoperable reflectance or radiance, or do we think a little higher level and think about NDVI, UVI, or do we even want to think a little bit higher level than that as well, in terms of how do we deliver to users data that they can use interchangeably? I know if we start thinking about like HLS as kind of that meta constellation, and we start throwing in more and more constellations into that greater meta constellation, how do we track and keep those time series for either a given spot as a function of time consistent, or how do we think about what's the meaning behind NDVI that we want to really tease out, and is there maybe a land cover phenological phase kind of dependence that we want to also factor into NDVI? And I'm really getting at the heart of kind of what I can think of as interoperability between the different satellites in that meta constellation.
So one answer is that so I'll take the HLS case where we've tried to fix the band passes to a Landsat reference. And so in theory, we have a physical measure, which is the reflectance as Landsat would have measured it at that time. If you have an uncertainty about each measurement, then you could propagate that uncertainty through things like Monte Carlo analysis, right? I mean, if you're taking that reflectance data and you're turning it into NDVI, and then you're going to turn that into a crop productivity model, right? You actually could, if you know that distribution of error, model the range of possibilities you could get out of your end modeling, based on that uncertainty. We rarely do that in remote sensing, right? People do that in the modeling community all the time, but we don't do it with our remote sensing products very much. We probably should. And that's why you have per pixel uncertainties. It would be a great thing to do, computationally intensive.
I think something interesting that came up in all conversations is this idea of model-based interpretation of the data. And I think it's something that is hinted at, but we're not going all in like you see in other disciplines, where people would treat uncertainties, not only the radiometry, going back to the band passes, that's just another form of uncertainty, right? It's a spectral uncertainty. So all of this could be modeled in a Bayesian way and just incorporated into your model. And if the model is physics-based, then physics is always interoperable, right? So.
Questions from the floor? Let's just get different people. Following on that conversation about interoperability of the data, and the replies and the discussion was mostly about it's what my sensor can measure, as opposed to what are we trying to ascertain about the environment, and the physical phenomena, the geophysical aspects across different ways, different sensor measurements. There's climate data records and environmental data records which aim to get after that definition of the physical phenomena that we're of interest we have interest in, and then seeing if we can get sensors to actually get some continuity with respect to that. It strikes me as maybe that's a way to get after more the interoperability between the data sensor, between the data.
At a higher level.
At a higher level. Yeah.
So what questions do you have for each other?
I have
a related question about this calibration or cross-calibration of sensors. How much effort have you spent, or how much have you tried to see whether there's any bias in the cross-calibration regressions or whatever formulas you're using, where your training would be would show that this calibration really fails in some environments or in some conditions, and if you have some examples where the cross-calibration does not work.
So Landsat, in terms of radiometric calibration, I mean, Landsat and Sentinel have been looked at pretty carefully together. And Farhan is here, and he's going to give a talk later, so I think he's probably the best person in the room to talk about that. Yeah, generally they seem to be well calibrated and well calibrated to each other. So, but you're asking something more specific.
Yeah, what I'm getting at is most of the error descriptions we get are across the whole data set.
Right.
But maybe in your training or your validation data set, you had 2 points of a marsh that has a specific spectral signature, or of regions which are often covered with a lot of water vapor. And is there some way of estimating whether my specific area that I'm looking at, like something in South Africa, is an area where this calibration will be problematic, or whether it fits nicely with your model of cross-calibration?
Yeah, it's a good question. In terms of the higher level products like HLS, reflectance, you know, the atmospheric correction definitely does not perform as well in some environments as others. So we know at high latitudes it doesn't do very well. We know cloud masks often fail over urban areas, right? So you're right, having a catalog of those sort of problematic areas and themes I think would be really useful. But yeah, it's not done really. So.
Well, it's always an issue of validation too at some point. You know, if you have in situ observations for every point of their surface, then calibration is not an issue. But it's, you know, for example, with the Modus Fire product, it took us 4 years to validate 1 year of fire data. It's, you know, we can't keep up with the speed with which we generate the products. So I think that you know, it's the validation is always something to keep in mind in terms of comparing between data sets. If you have, you know, 4 data sets, you have one validation data set to look at all 4 of them, then that's a simpler problem than if you're trying to maintain the quality of, you know, or the validation of one data set every year through time. So it's, you know, if you're familiar with stages of validation, you know, stage 3 versus 4 and stage 2 validations, you know, it's the higher level of validation you get, the more intensive it is to do that validation, but also the more robust your product will be.
So one of the interesting things that was shown was the incredible increase in adoption of Landsat data after it became free. What is necessary to start integrating non-free data sets into these type of homogenized systems? And that could either be PlanetScope, or it could be USGS, for whatever reason, decides to start charging again.
Curtis?
How do you answer that question? To be honest, I think, and I hope we're to the point where we aren't going to bother to go that way. Meaning individual investigators aren't going to have to pay for the data that they use. And I don't know if there's a model that allows for a data buy from Planet, for example, that would put data in the public domain that many people could use, or something like that. But I think we're past the point where, particularly in the science and applications domain, that individual users are going to add to their data sets by buying data.
Thanks.
You mentioned that you had a 5-day latency on the HLS production because of the atmospheric correction. because you were waiting for some parameters that you needed. So it's not driven by computational time, it's driven mostly because you're waiting for this. Yeah, it's very high.
I can repeat
There you go. So I'm asking about, he said, your name is
Jeff.
Yeah. That there is 5-day latency, in the production of the HLS datasets because some parameters needed for atmospheric correction, some weather data, I presume, needed to arrive, and that was driving the latency. Just a bit more detail on that.
I think it's the ozone and the water. It's the ozone, really, that we use. And that's what's driving the latency right now.
Mm-hmm.
It's usually better than 5 days, but we're just promising 5 days.
Where are you getting it from?
It's from NSEP,
Okay.
NOAA reanalysis data, and they get it from satellite.
Yeah, for sure.
EPCOMs and stuff, yeah.
So yesterday, the folks from Cosmic were talking about SpaceNet and these data science, like this, they're reaching out to an audience of more general data scientists working with satellite, that start to work with satellite imagery. I was wondering, from your guys' perspective, what kind of data would you give those people for them to, or what you think should be given to those people for them to work with in a meaningful way?
I am trying to remember back to exactly what they were talking about.
Well, okay, so their particular example was a contest for building footprint, or building footprint detection. But the general, that's one application of being able to derive certain information from satellite imagery. And the audience that they're going for, I believe, and somebody else in the room can correct me, are perhaps more kind of generalist data scientists, computer vision folks that may be relatively new to satellite imagery, but are good at other stuff. From the perspective of folks that are deep into satellite imagery, it's interesting.
I'll say that, there's a big distinction in my mind, at least, between the very high resolution focus, because that tends to be on object recognition, right? And things like e-cognition or whatever, where you're mapping objects out on the ground. And then what we do in the Landsat and the MODIS world, which tends to be pixel-based, right? It's sort of divvying the world up into pixels and looking at the spectra of pixels. And maybe that's an old-fashioned way of looking at that difference. You can certainly combine those two worlds, but they are a little bit different. So in terms of the stuff that you were talking about yesterday, it's really focused on object recognition. We don't do so much of that in the Landsat world at this point.
Do you see a role for the data scientists?
I see a role for time series analysis. I think we've just started in time series analysis, and with an analogy back to, there are people still for machine learning who are improving image classification algorithms, and we've been after that for 40 years. And with time series analysis, we've just really gotten started. And so there's all kinds of opportunity for innovation and improvements in that domain.
And I would say with the high res, it's it is sort of a different problem that we're starting to adapt to in remote sensing. But when you start to get into that domain of object recognition and working not with pixels but with objects, in remote sensing we're actually pretty far behind other fields. So if you look at the medical imaging literature, the computer vision literature, there's a lot of good methods there that are slowly starting to migrate into the remote sensing world. But I think in terms of data science, those are the types of methods that maybe make more sense for those types of problems.
Yeah, I actually jumped up here to kind of comment on that. I think so. I lead a team of data scientists that uses remote sensing data, and we've built both models that are object detection and models that are purely pixel based. And it's to me like making that decision on how best to model, it really depends on the problem. So I think there are a lot of opportunities in data science that are purely pixel-based. And like a good example is, we have training data where, they have gone out and taken field measurements to like classify the tree stand and the, fraction of pines versus, cedar or whatever in forest. And you can use remote sensing to like directly predict, like, can you tell differences? Maybe not with Landsat, but with higher resolution data. So I think there's definitely opportunities. Time series, I think, is like something that comes, we're hearing clients that are really interested in this change detection type of problems, and I think machine learning has good applicability there. The second comment I wanted to make actually goes back to this idea of cross-sensor calibration, because again, on the machine learning side, this is like a feeling I have, and I'd like other people's opinion. How many people here have built machine learning models on remote sensing data? A lot. Do you guys feel like absolute calibration is as important as relative calibration? Yes? One hand. So, but this is a topic. Like, I think that there is room for discussion on whether or not that cross-calibration is really needed, or if you let the analytics take care of those offsets. And it all really depends on, like, are the propagated errors small enough? So I think this, like, goes back to your talk, and that is what you are doing. It doesn't matter that they're not the same. You can still use them together. And I think machine learning has opportunities there. So.
And back to the data science question, there's also this sort of long-standing split in remote sensing between physically based and empirical or data science approaches, right? I mean, I was sort of groomed among physically based people who said, okay, you must calculate radiance and then go to surface reflectance, and then you propagate that through a canopy reflectance model, and you calculate your leaf area index based on that, right? But that's very different than a machine learning algorithm, right, where you're essentially training non-parametric way. But both have absolute relevance. Usually the statistical stuff outperforms physically based.
I think it seems like
causes a physicist to stamp their feet on the ground.
I think a lot of people here have their feet in both camps, and
Right.
that's what, like, I certainly am that way, and I get kind of excited just listening to people kind of throw out ideas here, because I think we're kind of getting to trying to make the best of both worlds.
Right.
We run out of time.